It is my pleasure to welcome you again to this course on CFD. Today is the last class for this week. Previously, we have done detailed procedure for direct methods as well as iterative methods. There are some difficulties while employing iterative methods. In today's class, we are particularly going to see what difficulties will be there and how to overcome those difficulties. There is a procedure called preconditioning, and today's class we are going to talk about different preconditioning and how to check what kind of preconditioning to be done. Need for a preconditioner: the convergence rate of iterative methods depends on properties of the coefficient matrix of the linear system. For example, if the coefficient matrix A is ill conditioned, then convergence of the iterative methods becomes very slow. And for large sparse matrices, which usually happens when you deal with PDE for fluid dynamics or heat transfer, it is usually difficult to compute or solve such situation with the help of LU decomposition. In those situations, we follow a procedure called a preconditioner. A preconditioner essentially transforms the original system A x equal to B into an equivalent system which has almost the same solution as what it be for the original system, and that equivalent system is easier to solve and it has better convergence rate. Let us get some more idea about this preconditioning. A is the original coefficient matrix, and let us use letter symbol m for preconditioner. Then we find inverse of the preconditioner m as m inverse. Then you find product of m inverse A and condition number for that product matrix. Then the convergence rate is governed by the condition number of the product matrix, that is m inverse A. The choice of m should be such that the condition number is reduced without increasing the cost of solving the system with m. For instance, if A x equal to B, then matrix m is as close as A in such a way the transformed system m inverse A x equal to m inverse B has the same solution as the original system A x equal to B, but the spectral properties of its coefficient matrix m inverse A may be more favorable for transforming the system and getting the solution. The nature of the system of equation, that is whether it is well conditioned or ill conditioned, is important to trust the accuracy of the solution. Another criteria to trust the accuracy of solution is what is known as a condition number, and that is based on what is known as a RowSum norm. Now, let us explain what is RowSum norm and how to obtain condition number. To find the RowSum norm, sum of absolute values of the elements of each row of the matrix A. The maximum out of such values is what is known as a RowSum norm of that particular matrix A. In terms of expression, it is shown here. So, you find for the coefficient matrix A corresponding elements, you sum them up for j going from 1 to n, and you take the maximum of all the rows, and that becomes a RowSum norm of the coefficient matrix A, and it is mathematically given here. From that RowSum norm, it is possible to find or define condition number as product of RowSum norm of coefficient matrix and RowSum norm of its inverse. So, for the given matrix A, you have one RowSum norm. If you happen to do an inverse of it, that is A inverse, you have another RowSum norm for that particular inversed matrix, and you take a product of it, that will result in what is known as a condition number. In the last slide, I mentioned about condition number RowSum norm. We will now explain or get an idea of this definition with the help of a matrix. Before going to the detail, let us first understand what is ill conditioned and well conditioned system of matrix. For example, you consider a system A x equal to B. This system can be either well conditioned or ill conditioned. Let us get an idea of what is well conditioned or ill conditioned with the help of an example. Well conditioned system, the definition: any small change in the coefficient matrix A or the right hand side matrix B will lead to only a small change in the solution vector x. Consider the system A x equal to B, where coefficient matrix A is defined as with the elements 1, 2, 2, 3 and solution vector x as x and y, and then right hand side vector B as 4, 7. If you solve this, you get answer as x y equal to 2, 1. Now, what we do? We make a small change in the coefficient matrix as shown here. Instead of 1, it is now 1.001. Similarly, other elements as 2.001, 2.001, 3.001. The solution vector remains the same. The matrix on the right hand side also remains the same. For such system where there is only a small change in the coefficient matrix, solution will look like this: x and y equal to 1.999 and 1.001, and you can observe that these values are very close to the original value of 2 and 1. Let us take the other case where you make a small change in the right hand side matrix, and that is what is shown here. So, coefficient matrix is the same. The right hand side matrix, now it is 4.001 and 7.001. For such system, solution appears to be as shown here: x and y equal to 2.003 and 0.999. So, you can observe for this example, if you make a small change either in the coefficient matrix or on the right hand side matrix, it results only a small change in the solution matrix. Let us take other example to understand what is ill conditioned system. In the case of ill conditioned system, any small change in the coefficient matrix or the right hand side matrix will lead to a large change in the solution vector. Consider again an example matrix as shown here: 1, 2, 2, 3.999 and x y as a solution vector equal to right hand side as shown here. Solution of this system is as shown here: x and y equal to 2 and 1. We take the first case, we change the coefficient matrix slightly. So, instead of 1, 2, 2, 3.99, we get 1.001, 2.001, 2.001, 3.998. Right hand side matrix is the same. Now, for this system, solution appears to be as shown here: x and y equal to minus 3.994 and 0.001388. You can observe here this value is very much different from the original solution value. Let us take the other case where we change the right hand side matrix, and it is shown here B as 4.001, 7.998, right. The coefficient matrix is the same. Now, for this system, solution matrix appears to be as shown here: x equal to minus 3.999 and y is equal to 4.0. Once again, you can observe by comparing solution matrix for this system with the original system, there is a very big difference, and this kind of a system is what is called ill conditioned system. Now, let us go to the definition of RowSum norm and try to explain. Consider the matrix A as shown here with elements 10, minus 7, 0, minus 3, 2.099, 6, 5, minus 1, 5. We define RowSum norm as a maximum of summation of rows, and we take the magnitude of the elements to calculate RowSum norm. and formula wise it is shown here, and this is infinity norm equal to summation sign, and in this case we have 3 rows. So, j is equal to 1 to 3 and we consider each element and we take the magnitude for each element for all I. Now, for this example matrix we try to apply this definition. So, max of first row 10 minus 7 0 and that is what is shown here. Second row minus 3 2.0996 and that is what is shown in the second bracket terms. Third row is shown in the third bracket term. Now, you find the summation and you find maximum is 17. So, the RowSum norm infinity norm for this matrix is 17. Let us find out how to do condition number. For this we take another example matrix, simplified matrix. A has 1 2 2 3.999. Now, inverse of this is minus 3.999 2 2 and minus 1. So, we find RowSum norm of the original matrix 5.999 and RowSum norm of the inverse matrix as 5.999. Now, for the condition number is a product of RowSum norm of both the matrix. So, as defined here, condition number of matrix A equal to RowSum norm of original matrix multiplying RowSum norm of the inverse matrix. So, we substitute the values and we get value as 35.998. So, we explain with the help of example coefficient matrix RowSum norm and how to get condition number. Now, we proceed to know about different preconditioning available. The choice of preconditioner M should have the following properties. Its use should entail low memory requirements, it should not add to additional memory, its inverse should be easily obtainable. Please remember, we want to do preconditioning because original coefficient matrix there was a difficulty in getting the inverse. We multiply the original coefficient matrix A with preconditioner M. The preconditioner M should be easily inversible. Then the transformed problem should converge faster than the original problem. Different preconditioning techniques are available such as left preconditioning, right preconditioning and split preconditioning. Common and simple methods to arrive at M. First one, Jacobi preconditioner, where the diagonal element of the coefficient matrix A itself is a preconditioner. So, M is a symbol we are using to identify it is a preconditioner. So, it is possible to use the diagonal elements of the original coefficient matrix as a preconditioner, and such method is called Jacobi preconditioning. The second one, Gauss-Seidel preconditioner, where the lower plus the diagonal is used as a preconditioner M. The third option available, symmetric Gauss-Seidel preconditioner, and M in such case is given by this expression where D plus L multiplying D inverse and then D plus U. Then last one is successive over relaxation preconditioner SOR, where M is defined with the product of 1 by omega multiplying D plus omega into L, where omega is a relaxation parameter. There are other popular preconditioners available. For example, incomplete LU and incomplete Cholesky for iterative methods like BiCG step and conjugate gradient methods respectively. There is also another technique called multigrading technique, which is also classified under preconditioner. Choice of preconditioner is very important and it varies from problem to problem. So far we have seen matrix inversion procedure, direct methods, iterative methods and then preconditioning methods, which is helpful in the case of iterative methods. Overall, any system of equations, there is a procedure to get the solution. Problems in fluid dynamics and heat transfer involve solution of coupled system of equation, where you have a dominant or dependent variable appearing in every other equation. There are two approaches. In the first approach, all the variables are solved simultaneously, and this is called simultaneous coupled solution approach. In the second approach, every transport equation is solved until its convergence is reached. Then the next transport equation is triggered to get the solution. Such approach is called segregated approach. We will have some more explanation about these two methods. In the case of simultaneous approach, all the transport equations are solved simultaneously. For example, you have a force convection problem, where you have a Navier-Stokes equation and there is a energy equation. Both Navier-Stokes equation and energy equations are handled simultaneously. Solution of one immediately affects the solution of the other, and solution matrix obtained for such simultaneous approach is a block banded structure, and this method is chosen where equations are linear and very tightly coupled. I gave example of force convection heat transfer problem. In the case of segregated approach, when equations are nonlinear and complex, then it is advisable to go by solving one equation at a time, get a converged solution, then go to the next equation. So, equations are solved one by one until each one of them are converged fully or partially. While solving equation for one dependent variable, other variables appearing in that particular equation are assumed to be known either from previous iteration values or previous time level value. The whole cycle is repeated until all equations are satisfied to the convergence criteria fully. We also want to learn another procedure called under relaxation. Algebraic equation for any generic variable phi, whether you follow a finite difference or finite volume method, will finally have a form as shown here: A p phi p n plus neighboring node coefficients multiplying the variable equal to known value on the right side. In this p, the subscript p is used for node of interest. If you solve this equation, then you get phi at the node of interest p at the current time level n. Now, the question is whether to use that value as it is, or whether you can relax a little bit and then use it for the next iteration. Such procedure is what is known as an under relaxation procedure. So, this equation is a linear equation. Phi n is allowed to change by a fraction alpha phi in such a way as shown here. Phi n is equal to phi n minus 1, that is a previously obtained value minus alpha times the new value with the new old value. So, this difference phi nu minus phi n minus 1 will tell how much the difference has happened between last iteration or last time value with the current iteration or current time value. You take a fraction of it, that is what is given by the factor alpha, and you can add or subtract the old value, where phi nu is given by previous expression as shown here. Now, if you employ that under relaxation procedure in the linear system of equation, they get rewritten in the form as shown here, including relaxation factor. So, in programming it is easy, all that you have to do is explain alpha, the beginning of the calculation, then the values are adjusted according to the expression as shown here. First term on the left side and term on the right side are modified diagonal elements and source vector respectively. Alpha phi is called relaxation parameter. So, while solving equation you can appropriately define relaxation parameter for different variable. For example, velocity can have one value, pressure can have another value, and if you are solving for turbulent flow, k and epsilon variables can have another value. So, alpha is a relaxation parameter which varies for different variable. If alpha is less than 1, such a procedure is called under relaxation. If alpha is greater than 1, and the procedure is called over relaxation. It is different for different governing equation, and the value is decided based on different numerical trials and experience. So, in this week we have seen matrix inversion procedure. There are two methods, direct methods and iterative methods. We went in detail for direct methods, Gaussian elimination method, diagonal matrix algorithm, LU decomposition method. We also listed 5 methods under iterative methods, and we learned a technique called preconditioning technique to be used for iterative methods. We also learned couple of other things, what is known as how to proceed to get solution, segregated solver and simultaneous solver. There is also one more technique called under relaxation technique, which helps in fast convergence. With this we come to the end of this week class. Next week we are going to have a demonstration of a code, description of the problem, how a code is written and how to obtain different results. Thank you.